Alright, so we're used to graphs using Cartesian coordinates or rectangular coordinates or x and y coordinates. However, with polar graphs, you'll instead write your coordinates as r theta. So let's use this point as an example here. When you're measuring your, when you're finding your x and y coordinates, the way you find them is you measure the distance from the origin to the point along the x-axis as well as the y-axis. And those are your x and y. However, when you find r is the distance directly from the origin to the point. Also, when you are talking about the origin, like in polar graphs, you usually refer to it as the pole. So this is r. Theta is the angle between the positive x-axis and the line of r, right here. Alright, as you can see here, x, y, and r all form a right triangle, right? So, and that makes you think of the Pythagorean theorem, but instead of using a squared plus b squared equals c squared, you'll have x squared plus y squared equals r squared, right? This is one of the equations that you use when you're converting between polar and rectangular coordinates. The other three, which involve theta, because remember it's a right triangle, you can use trigonometric functions. So you can have sine theta equals, opposite over hypotenuse, so it would be y over r. You have cosine theta, adjacent over hypotenuse, so you would have x over r. And you'd have tangent theta, opposite over adjacent, so you have y over x. So you can see that in this example is the points, like the x and y coordinate would be the point 4, 2. Alright, so to convert this rectangular coordinate to polar coordinates, you can see that you have your x and your y already, as we figured, and you can plug those in to solve for r. So you have 4 squared, 16, plus 2 squared, 4, is r squared. So then you have r squared equals 20, which basically gives you r equals the square root of 20. So to find theta, you can use your tangent theta equals y over x equation because your r is the square root of 20. That's a little nasty to use. So we can just write tangent theta equals y over x 2 over 4. We can simplify that to 1/2. And then theta would equal the inverse tangent of 1/2. So put in 0.5, and then the inverse tangent of that would give you about 0.464. So the rectangular coordinate 4, 2 is the same as the polar coordinate r theta, or square root of 20, 0.464. Alright, so now we're going to have an example going in the opposite direction. We're going to convert from polar to rectangular coordinates here. We're going to name that point there on the graph about 2 pi over 4. Now, because we actually only have r and theta here, we don't have our x and our y, that's what we're looking for. You have the opportunity here to use the two equations we didn't use before, which are sine theta, sine theta equals y over r, and cosine theta equals x over r. Now I can rearrange those so it's r equals x cosine theta and r equals y sine theta. Alright, so using the two equations we had before, we'll find x first. X equals r cosine theta. All you have to do is plug in your r and your theta. So you have x equals 2 times the cosine of pi over 4. And that will give you 2 times square root of 2. over 2. So your x will equal square root of 2. Then you can do y equals r sine theta. It's just another matter of plugging stuff in again. So you have 2 times sine of pi over 4, once again, is the same thing, square root of 2 over 2. So then you just have y equals square root of 2. So then your polar coordinate 2 pi over 4 is the same as the rectangular coordinate square root of 2, square root of 2. So this might seem a little odd of me to mention, but just when you're writing polar coordinates, be careful not to mix up the order and write theta r. I know that seems silly and obvious, but I've found myself to do it quite a bit, so just be careful about that. But a major difference between rectangular and polar coordinates is that rectangular coordinates can only be written one way. The point 3,2, for example, can only ever be the point 3,2. However, as you can see here, this point r theta, this is the angle theta, but you can get this same angle by going around in the negative direction or going all the way around, and just infinite amount of ways you can get that same angle. So the way this is written as a rule here is the point r theta would be the same as r theta plus 2n pi, n being a positive integer, which basically says that no matter how many times you go around, you can get the same angle as theta. And now this one, negative r theta plus 2n plus 1 pi, this basically means, like, you see how theta, the angle theta, it kind of goes into the opposite direction. That's because negatives are not, they don't work the same way as they do with rectangular coordinates. Like, you know how this entire side of the y-axis would be negative x, and this entire side of the x-axis would be negative y? Well, because it's a radius, there isn't exactly a negative direction, except when you're talking about opposites. So when you go to this angle here, which would basically be theta plus some odd pi, which is why it's 2n plus 1 to ensure you get an odd number here. So for, like, say for instance, plus pi or plus 3 pi or 5 pi, you'll get this angle here. So then if you have negative r, it will go in the opposite direction from this angle, and you basically have r theta again. So for an example of this, let's use the point 4 pi over 2. So that'd be about here. One different way you could write this is you could add 2 pi to the angle, which would make you just go all the way around to the same angle. So 5 pi over 2 is a different way you could write this. You could also go to you could also add pi to go to the opposite angle. So you have 3 pi over 2, but you would need to go in your r would need to be in the opposite direction, so you would have a negative r. So another way you could write it is negative 4, 3 pi over 2. And just for one more way you could write it is you could use a negative angle, and instead you could do negative 3 pi over 2, which would bring you here, and you could have a positive r for this since it's in the same direction. So 4 negative 3 pi over 2. These are all different ways you can write the same angle, and there are many more. So now we're going to actually get to graphing polar equations. Right here on the screen right now are two basic graphs. Like, the first one is just r equals 3, which basically means that no matter what theta is, the radius will stay the same. So while the angle changes, like the radius is constant. So it's just a circle. You can also look at it as in the rectangular form. The rectangular form of a circle is x squared plus y squared equals r squared, just like the Pythagorean theorem thing that we use to convert polar coordinates and rectangular coordinates. So I can put 3 squared there. And this is just a line, basically. Theta equals pi over 4, because this time the angle is the one staying the same while the radius is changing. So like no matter if the radius is positive or negative, you'll just have a straight line. Like this, and this one just is basically y equals x. Now there's also like 2 more, I guess, more basic ones. Include secant and cosecant theta. Actually, let me write a secant theta and a cosecant theta. These will both give you vertical or horizontal lines. Now, like watch this one for example. You know how secant is basically 1 over cosine, so if I want to find x, remember x is r times cosine theta, so it would be a secant theta times cosine theta. The secant theta and the cosine theta would cancel out, so you would just be left with x equals a. That would just be a straight line, right? Like, it would just be a straight line. Now, the same goes for this one, but you would find y. And remember, y equals r sine theta. Cosecant theta is the same as 1 over sine theta, so they would cancel out, and you would have y equals a, which would just give you a horizontal line. And like these lines are at a. So now we're going to do a more difficult problem, r equals 4 cosine 3 theta. This graph can be like shown over the interval from 0 to pi. So we're going to plug these numbers into the equation and get 4, 0, negative 4, 0, 4, 0, and negative 4. This graph will basically look like this. Wow, this should be in art class now, actually. This obviously is not to scale in the slightest. These should pass through the origin. I should just do it over. I'm going to do it over. So the graph will basically look something like this. I'm not using that. The graph will look a little like this. That's literally the best version I will be able to ever draw of that. You can see here like that the radius starts at angle 0, 4, and then it shrinks down to 0, and negative 4, and then back to 0, and 4, and then back to 0, and then it will grow to like negative 4, but remember it's at the angle pi's, so it'll be opposite. This is called a rose curve, and there are other types of graphs that we'll get to later. So now we're going to do slope and tangent lines. You need the derivative to find both of those things, so we're going to have to find that. If you remember that x equals r cosine theta and y equals r sine theta, you can remember that r is a function of theta, so r can be rewritten as f of theta. So I'll write both of those while replacing r with f of theta. So you can take the derivative of both of those and find dx d theta and dy d theta. Of course, you'll need to use product rule for that. So when you take the derivative of x, you'll get dx d theta, which equals negative f of theta times sine theta plus f prime of theta times cosine theta. And you do the same for y, and you get dy d theta equals f of theta times cosine theta plus f prime of theta sine theta. And now it's a simple matter of putting dy d theta over dx d theta to get dy dx. And of course that's the derivative as we are used to it. So dy dx will equal f of theta cosine theta plus f prime of theta sine theta over negative f of theta sine theta plus f prime of theta, f prime of theta cosine theta. And this is your equation for the derivative of a polar graph. An important thing to note is that where dy d theta is equal to 0 and dx d theta is not equal to 0, there is a horizontal tangent there. But I have to stress that and, because they must both be true for there to be a horizontal tangent. The opposite goes true for vertical tangents when dx d theta equals 0 and dy d theta does not equal 0. There is a vertical tangent. However, when they are both 0, then you cannot make the mistake of assuming something. You cannot figure anything out if they are both 0. It tells you nothing. So for our first example, we'll find the vertical and horizontal tangents of the equation r equals cosine theta. As you can see, that's just a simple circle. Now, since it's a circle, there's going to be a horizontal tangent here and here at the top and bottom. At the left and right sides, there will be a vertical tangent, right? So now we can use the equations for x and y, x equals r cosine theta and y equals r sine theta, and plug in our function cosine theta for r. X will come out to be cosine squared theta, and y will come out to be sine theta cosine theta. You find the derivative of each, and dx d theta will come out to be 2 sine theta cosine theta, but that can be simplified to sine 2 theta thanks to double angles. And dy d theta will come out to be cosine squared theta minus sine squared theta, but that can also be simplified with double angles to cosine 2 theta. When you solve for theta, here you'll get 0 and pi over 2, and here you'll get pi over 4 and 3 pi over 4. Now, since you can see that they don't share any factors, then you know that where x equals 0, or excuse me, where dx d theta equals 0, dy d theta does not equal 0, and vice versa. So you know that here, where dx d theta equals 0 and dy d theta does not equal 0, there are vertical tangents. And at these two thetas, where dy d theta equals 0 and dx d theta does not equal 0, there are horizontal ones. So then you can plug in thetas to, you can plug in thetas to your original equation, r equals cosine theta. So when you plug in 0 to r cosine theta, you get 1. So 1, 0. And when you plug in pi over 2, you get 0. So you'll have 0 pi over 2. And at these 2 points, there is a vertical tangent line. And then you can do the same for these two. And when you plug in pi over 4 to cosine theta, you'll get square root of 2 over 2 pi over 4. And when you plug in 3 pi over 4, you'll also get square root of 2 over 2. and at these 2 points you will have horizontal tangent lines. So to finish off the lesson, I'll show you some graphs that you should get yourselves familiarized with. A plus or minus a cosine theta or a plus or minus a sine theta, these are called cardioids. Kind of shaped like a heart, as you can see. A plus or minus b sine theta or a plus or minus b cosine theta, these are called limasomes. If a is less than b, then it will have an inner loop and the graph will contain the origin, like this one here. But if a is greater than b, it will not have an inner loop and it will not contain the origin. If you remember the graph from the previous example, the rose curve, then this will show you some more specifics. R equals a sine n theta and r equals a cosine n theta are the different ways you can write this. N must be greater than or equal to 2 though. So if n is odd, then the curve will have n amounts of petals. So like the example we had before was 3 theta, so it has 3 petals. However, if the n is even, then it will have 2n petals. So if say it was 2 theta, then the graph would have 4 petals. So that's all I have to tell you about polar coordinates and polar graphs, so thanks for watching.